तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were looking at objectivity. If you remember, we had looked at, for example, how acceleration behaves when there is a change of observer, or under two observers, how acceleration would look like. So we had seen, for example, A star in terms of A, and we recognized that number one, that the accelerations, and of course we did before that velocities, are not material frame indifferent quantities. If at all they have to be material frame indifferent quantities, then A star should have gone through the transformation like this, A star is equal to QA, but since they are not like that, and then you have additional terms, we recognized that acceleration is not a material frame indifferent quantity. In fact, if you had noticed, the major reason why acceleration is not material frame indifferent is because of the fact that both C and Q, both of them are functions of time. Okay, both of them are functions of time. So in other words, we have allowed the observer, the second observer, the starred observer, not only to be different, but also allowed him to do what he wants, move with respect to time, and rotate, that is the Q, to vary that Q also with respect to time. That is very important. So that is the reason why we have acceleration to behave in that fashion, and we recognize that some of them are quantities which are known. Say for example, this is the Coriolis component, and that is the centrifugal force, and the other one is called as the, this is called as the Eulerian accelerations, and so on. Yes, there are before we proceed, just a point of comment, but there are some constitutive equations been put forward, for example, which analyzes asphalt and other things, where you make some conditions. You say that the constitutive equation is not valid if Q is as a function of time is given to the observer. Okay, in other words, you say that I am violating material frame indifference. Okay, I am violating it, but violating and putting it in this fashion, and that what I am violating is actually the observer's motion with time and so on. That is also done, but I am not sure whether that is the right approach, because there are difference of opinion as far as this is concerned, and anyway, people have done that as well. So if you come across such kind of work, please understand that there has been a violation of material frame indifference, and so you have to take that a bit more carefully, and when you do analysis, that also should be taken into account. Okay, so and we also recognize, for example, that if this part is 0, then we say that the transformations are Galilean, these are Galilean transformations, and there are what are called as Galilean frame invariants. Let us not worry about that, but we will only worry about material frame indifference as it is applied to continuum mechanics. So let us just summarize with the fact that these are the types of changes that would take place between the start and the unstarred coordinate system. Now let us look at certain quantities of interest to us and see whether these quantities can take part in the type of constitutive equation which we want to build. Now first of all, let us understand how F would transform, or in other words, what is the relationship between F star and F? What do you think would be the difference, or what do you think would be the relationship? I had made a comment yesterday, and that comment is very much important. Note that f is defined as dou x by dou capital X, or the deformation like that. And note that when we define f star, and this as a philosophy is defined in such a fashion that the reference configuration is the same for both the observers, or in other words, f star is dou chi dou capital X, okay, or in other words, this is a function which is written like this, or in other words, this is written as dou small x star by dou capital X. Note that both of them are the same. So how does this transform? So you can write, say for example, f star to be dou x star by dou x into dou x by dou capital X. And knowing the fact that x, I mean of course you know all of them are vectors, and knowing the fact how x star and x vary, we had seen already x star is equal to c plus qt of x. So knowing that f star is equal to qf. So actually this is one of the things which I want you to notice, that f star does not vary as qf q transpose, which you would have expected because it's a second order tensor, but varies as qf only, and this doesn't exist. There have been variants of this definition. For example, people who follow Ogden, okay, nonlinear elasticity book, you would have found that he does not accept the fact that both the observers have the same reference coordinates. In other words, he says that it is possible for you to have two different reference coordinates, okay, for two different observers, in which case you will get one q here and q transpose here, but he calls this as qt, a q transpose initially or at the origin. Okay. But in most continuum mechanics literature, you will find that the observer has the same, or two observers have the same x or same reference configuration. Very important to understand that, and hence q varies, or f star is equal to qf is, or q is the only thing which is responsible for variation of f. So this is also called as 2-point tensor, if you remember, and so 2-point tensors transform in this fashion. So what is another 2-point tensor which probably you remember? First PLO Kirchhoff stress, okay, first PLO Kirchhoff stress is, so the same way P star is equal to QP is how it varies. Is that clear? And what about determinant of f? What would happen to determinant of f? Must be same. Very good, because it's a scalar quantity, and one of the things which we have said is that the scalar quantities are not affected. Suppose this is what we called as temperature, so T star is equal to T, and so the temperatures, whatever or whoever takes it at a point, is the same. So T star is equal to T. The same fashion, determinant of f does not vary, okay, and so you have the same factor. Now the other thing is there are other important quantities. Okay, let's see how that works out. How does, say we had already seen, say for example, f is equal to Ru. How does R vary and how does U vary with the observer? Let's see how can you work it out. So in other words, we have f is equal to Ru and f star is equal to R star U star. What is the relationship between R star and R, U star and U? So that's the question. So we have, start here, f is equal to, or f star is equal to qf, right, and that is equal to qru, or in other words R star U star is equal to Q R U. Look at that carefully and can you pass some judgment on that? R star U star is equal to Q R U. Very good. So from this what would you R star, very good. So R star is equal to QR. It also stems from the fact that this can only be decomposed in a unique fashion. If you remember, we had talked about this decomposition theorem and we said that the decomposition has to take place in a unique fashion. Okay? So this also means that, since the uniqueness means that there has to be a line which separates out, okay, the rotation part, the stretch part, the rotation part being unique. So R star has to be equal to QR. And that throws up a very important relationship, that what? U star is equal to U. Note that yesterday we had already commented that the quantities which are to be referred to the Lagrangian coordinates transform in such a fashion that they remain to be the same. So for example, we said that the Lagrangian quantities, start quantities, is equal to the Eulerian, the unstarred quantities, not like the Eulerian transformations. So this means that U star is equal to U, and that's what we are going to use in E. Okay, you will see that E star is equal to E. So what is the yes, why is U star is equal to U? You can see right away from the uniqueness theorem that R star is equal to QR. Okay, so there has to be a unique decomposition. Okay, hence you see that R star U star is equal to QR U, both of them, if they have to be the same, then the rotation parts have to be the same. So R star is equal to QR and the stretch part has to be the same. So U star is equal to U. So in other words, the Lagrangian parts remain the same for the two observers. That's what I said, it doesn't change. This also stems from the fact that F star is equal to QF, or in other words, the reference configurations are the same for both the observers. Okay, so hence U star is equal to U. Okay, what happens to the other quantities? So for example, how does sigma transform? Can you work it out? How does sigma transform? The clue is that sigma is equal to, can be written as T is equal to sigma n. T is equal to sigma n. Of course, sigma transpose equal to sigma is what I take. So T is equal to sigma n. Let us see how we work out for sigma. Note that, in other words, you can write T star is equal to sigma star n star, and the fact that T and n being vectors, okay, and that they transform according to the vector laws, and hence you can say that Qt is equal to sigma star Q n. Okay, in other words, Q sigma n is equal to sigma star Q n. Comparing the left hand side and the right hand side, I can say that Q sigma star Q, and noting the fact that Q is an orthogonal tensor, so Q inverse equal to Q transpose, Q sigma Q transpose is equal to sigma star. So what does this say? This says that, what does it say? That Cauchy stress is objective. correct, is objective. So that's a very important thing. So Cauchy stress, that's the reason why we use Cauchy stress in the constitutive equations without problems, because Cauchy stress is objective. Okay? Fine. So what about two other quantities which are of interest to us? Say what would happen to, say for example, we had two more quantities, L, D, and of course W. So what happens to L, D, and W? Are they material frame indifferent? So in other words, can I use L, or what should I use in the constitutive equations? And more importantly, even before we go here, we have to establish a simple fact that the rate of stress, sigma dot, is one of the quantities that is extensively used in the constitutive equations. Sigma dot, okay, that is time derivative of sigma. Okay, these are what are called as, there are what are called as rate type constitutive equations. Okay, very much useful in many circumstances, including plasticity. So can I use sigma dot? You remember that in plasticity we simply divided it by dt and said d sigma by dt, which is sigma dot can be used as very easily instead of d sigma as well. Remember that we did that for lambda dot and so on. So sigma dot is one of the quantities which are extensively, I won't say used, because we are going to say that it's not going to be used. Okay, is a quantity which is very useful if it is possible to be used in the constitutive equations. Okay, so let us see whether you can use it. Can you just check that and tell me? Check whether sigma dot, take that equation, first equation, check that and tell me whether it is possible to use it and why it is not possible to use it. Very simple. There's nothing that we need to do much. See, what we have to do is only to differentiate this equation with respect to time, so that you will get, say, q dot sigma q transpose plus q sigma dot q transpose plus q sigma q dot transpose is equal to sigma dot star. So obviously this equation tells us that because of the fact that q is a function of time, okay, sigma dot is not an objective quantity, and we have to do something else in order to make sure that sigma is an objective quantity. Okay, so sigma dot rather is not or cannot be used in the constitutive equations. Is that clear? Okay. Yes.
Using the same yield criteria for both sigma and sigma star?
Yes. Are we using the same yield criteria? Yield criteria doesn't come into the picture here, because we are only saying what you are going to use in the constitutive equation. Yield criteria is different. See, what we are trying to say is, what is the quantities which can be related by means of an equation which we call as constitutive equation. Can I relate, say, epsilon dot and sigma dot, or E dot, or epsilon dot and or D and sigma dot? Okay, can I relate D and sigma dot, this sigma dot here, in a constitutive equation when rate of loading becomes important, say, for example, or where and many of the nonlinear equations are written in a rate form. Rate form means that the derivative with respect to time goes into the constitutive equation. The constitutive equation is, for example, is not written as sigma is equal to E epsilon. It's not written like this, but is written sometimes, most of the times, as sigma dot is equal to Et epsilon dot. This is how it is written. If you write it like this, okay, is that equation correct? For example, you remember that we had all the time wrote d sigma is equal to Et into d epsilon. So can I just convert this into a time derivative and write that as sigma dot is equal to E t epsilon dot, okay, or d dot, and go ahead, or sorry d rather, go ahead. No, this can't be done because sigma dot cannot be used in the constitutive equation. See, as long as we are talking about very small deformations where the reference configuration and the current configuration are almost the same, which you would have followed in what is called a small deformation analysis, all these issues do not come into picture at all. We will not be looking at objectivity and all these things. These things, though note this, though you are not absolutely correct, but doesn't matter because all of them are infinitesimal deformations. Okay, but in these circumstances we are talking about finite deformation cases, and hence all these precautions have to be taken, okay, so that the results are consistent, the what you get is consistent not only with the theory but also with experiments, right. So let's move to L, our velocity gradient tensor, and D and W. They are going to have some role to play, which I'm going to tell you shortly. So what is, or how does L transform? Let's see, can you work it out? How does L transform? Okay, you know what is L? L is equal to F dot F inverse. What is the relationship between L and L star? L star is equal to what in terms of L? This is what we are looking for. So in other words, L star can also be written as F dot star F inverse star. We also have the relationship that F star is equal to QF. We also have the relationship that F star is equal to QF. So that F dot star is equal to Q dot F plus Q F dot. And note this carefully, that F star is equal to QF. Okay, I can take an inverse so that F star or F inverse star is equal to F inverse Q transpose, okay, Q transpose, by making use of the fact that AB inverse equal to B inverse A inverse, and that Q inverse equal to Q transpose, I can, so F inverse star is equal to this as well. So now substituting this onto this expression, this expression here, okay, this as well as these equations to this expression, okay, let us see what you get, okay, and then of course ultimately writing in terms of L, let's see what you get out of it. So L star is equal to, first term is here, Q dot F plus QF dot. The second term is here, that is F inverse Q transpose. So let's see. So the first term is, of course, Q dot Q transpose. Yes, Q dot Q transpose plus Q L Q transpose. Beautiful. So Q L Q transpose. So note that then L star is equal to Q dot Q transpose plus QL Q transpose, which means that these velocity quantity, of course, because it is a velocity quantity, okay, they are again not frame indifferent. They are not frame indifferent. Now let's look at W. Let us see what happens to W and D. What is the W? Right, we use the symbol W, right, for the skew symmetric part of L. Okay, that is D we had used, if I remember right, half into L plus L transpose. W is equal to half into L minus L transpose. Now let us see what happens to D first. If you want, you can do this D, okay, and then do the second one also. So D is equal to, so what is that we want to do? I want to know what is D star. D star is equal to half of L transpose, sorry, L star plus L star transpose. Now L star I know how it transforms. So you can write that down. For example, that is half into Q dot Q transpose plus the second term here, QL Q transpose. So QL Q transpose plus Q, so you transpose of this, so Q dot transpose plus, it will be the same, QL Q L transpose Q. Let us see what happens to this. Let us look at these two terms, Q dot Q transpose plus Q dot transpose. What happens to these two terms? No, very simple, nothing very difficult. Don't just take what is Q transpose. See, this is a trick which you have to play in every problem, most of the problems. Trick is very simple. Q transpose equal to I. Okay, note this trick. So nothing great, Q dot plus Q dot transpose, so that Q dot Q transpose is minus of Q dot transpose. So that means that those two guys are out. Okay, so you can take this out. These two guys are here are out, so that D star can be written as D star is equal to Q half of L plus L transpose Q transpose, that is Q D Q transpose. Right? Okay. Fine. Having done that, please do the W part of it. Do W, how does it transform? Now I have done D for you, just do W here. What you have to do is exactly the same thing. Now that just substitute for L star, and let us see what is your result. So in other words, W star, yeah. Now keep substituting. Look at that and substitute. Yeah, just 2 minutes. Let us see. So what do you get? W star is equal to Q, very good, Q dot Q transpose plus QW Q transpose. So you see that W again is not here, material frame in different quantity. Right, is that clear? Okay. So we have almost seen most of the things. You see that E is equal to E star, you can just prove that. So we know what are the type of quantities that we have to use, but we are stuck at one place where we showed sigma dot is not a material frame in different quantity. Right? We are stuck because we want some rate quantity which can be used in the constitutive equations. We do not seem to have it. Okay, can someone suggest what can be done? I will give you a clue. Okay, One is that we can now have combinations. It is not that every independent quantity has to be looked at whether it is objective or not. It is also possible to have a combination of quantities, and you would be surprised to see that a combination of quantities would be what I would call as objective. So let us take a vector, say u. So u dot minus wu. Suppose you take a quantity like u dot minus wu. Take a quantity like that, you will see that this quantity becomes objective. Okay, so it's not very difficult to show that. Or in other words, what we mean to say is u dot of minus wu star is equal to q into u dot minus wu. Okay, let's check whether that is true. In a similar fashion, you can check that, but in a similar fashion, you can also have a combination of sigmas to show that it is possible to get a combination of sigma to be, or sigma including sigma dot to be, material frame indifferent quantity. Okay, so these combinations are now used, okay, as objective quantities. They are given a very special name as well. Okay, check that. Okay, you check that, but meanwhile let me finish this part. That let us take now, as I told you, a combination of certain quantities. Let us take, for example, sigma dot minus w sigma plus sigma w. Let us take a quantity like this. Okay, it is not very difficult to check whether this is a frame indifferent quantity or not. Not very difficult to check that. Okay, so this quantity is used in the constitutive equations as a rate quantity instead of sigma dot, and is usually denoted by sigma with a circle on top. Yeah, that's what I said. You check that. I'm going to allow you to check that. It's very simple to check. What you have to do is to only substitute all those for w, what it is. But before I complete it, okay, before I go to that, let me introduce this. This is called as the Yeoman rate. This is called Yeoman rate. Okay, Yeoman rate is extensively used in large deformation plasticity. You can see that being mentioned in, for example, packages like Abacus manuals. You will see Yeoman rate. So what does Yeoman rate mean? Yeoman rate simply means that since sigma dot is not objective, a basket of sigmas and dots are taken. This whole thing is taken together. Okay, and that is used as the rate quantity, so that the quantity becomes objective. Okay, so there are in this sense there are a number of objective quantities. Okay, rate objective quantities. So these quantities are used as one of the members of the constitutive equation. Okay, so you can check this. But even before we do that, okay, to give a physical picture of this rate quantities, let us look at what is called as Oldroyd rates. Oldroyd rate is a Lie derivative of sigma. What is Lie derivative? We had already seen this. Pull back, do a d by dt, then push forward. Okay, that's called Oldroyd rate. So in order to interpret it, it's very simple to interpret Oldroyd rate. So what does it mean? We had already seen this. So what is Lie derivatives interpretation? That means that you remember what it is? So which means that we are now moving along with the velocity, all the twists and turns of the velocity field, and looking at how the sigma changes with time. So we are in motion along the velocity field, and we are then looking at the change in sigma. So for example, Oldroyd rate, I mentioned this because it's very simple to understand that way. So in other words, these rates take into account such motions due to q dot, okay, such motions they take into account, okay, or physically what it means is that you are also moving with that fields like that, you know, the q dot fields, okay, and then you are looking at the derivative, or in other words, the sigma dot, which was not a, why was that not a objective quantity? Because there was a q dot there, okay, q dot there. So that q dot is removed, okay, in this fashion. By grouping them together, that q dot quantity is removed, right. You can physically also you can look at it in a slightly different fashion. Suppose I have a bar here, okay, and the bar starts to rotate instead of you rotating, okay, the bar starts to rotate or the observer rotating. You can also imagine that the bar starts to rotate along with the stress field, okay. So let this rotation be defined by q of t, okay. So what my sigma dot relationship says is that the sigma dot in this case is a function of q of t, the rotation which is a function of time, the rate of rotation, or q dot of t rather, right. So that is the reason why sigma dot, in other words what it means is suppose I start rotating it at different, you know, qt varies and q dot takes different values, then my sigma dot will take different values. That's what it means physically, okay. Suppose you are in a situation where you sit with the field or with this and then start rotating in the same fashion and start measuring it, compensate for that q dot, then the ill effects of q dot are out, and the measurements that you would do are exactly the same. Is that clear? So that is what is achieved by this kind of what we call as the objective rates. Sometimes we call these rates as co-rotational rates, because that is that rotation effects, that's co-rotation, you are with that rotation, co-rotational rates. Okay, co-rotational rates, because these rates, that is this rate is called a co-rotational rate, okay, because these rates remove the ill effects of q dot. So what does it mean? Simply, I mean, preempting things you may look at later, it simply means that when I put down a constitutive equation, okay, I use, for example, I can put the constitutive equation of this form, say CTD, okay. So instead of sigma dot entering constitutive equation, you will have this co-rotational rates that enter into constitutive equation. Yeoman rate is not the only co-rotational rates. Oldroyd rate, see, is another rate. There are a number of rates like this, okay, depends upon what you use. Ultimately, what do you mean by co-rotational rates? There are two rates, co-rotational convected rates. I will not go into the details of it. I just want to pick only the principal philosophy, that it is possible to compensate for this q dot and get a co-rotational rate which can ultimately be used in the constitutive equations. Is that clear? Any questions? Yes. Oldroid rate, see people write this as old sigma. Okay. Oldroid rate is usually written as old sigma, sigma old. Okay. That is how you use it. Yeah. Why not you write down? Yeah, what is the expression? Why not you write down? That's one of the good things that you asked. So how do you write down Oldroid rate? Push back d by dt, then pull forward. So f d by dt of f inverse sigma f inverse transpose f transpose. So this is the Oldroid rate. So you expand that f into f inverse transpose dot sigma f inverse sigma f inverse transpose plus f inverse sigma dot f inverse transpose plus f inverse sigma f inverse transpose dot f transpose. So you will ultimately see that Oldroid rate is written as sigma dot, that's written as sigma dot minus L sigma minus sigma L transpose. This is the pullback derivative push forward. Okay. So this sigma is pulled back. You go and have a look at our old notes. Pullback derivative, then these two are the push forward operations. Note that stress, if you remember, we had two operations for two different quantities. For contravariant quantities and covariant quantities, we said that the pullback operations are different, okay, and push forward operations are different. Operations are different in the sense that the equations are different, and sigma being contravariant quantity, okay, the pullback and push forward is different from what you would do in the case of, say, for example, strains. So the meaning becomes clear here at this part, right? So Oldroid rate is another rate that is used in the constitutive equation. Of course, when you use different rates, then the C quantity is different. They are not the same. You have to be careful in that as well. Okay. So of course these are not the only rates. Okay, as I told you, there is what is called Truesdell rate, okay, which is again very popular. Truesdell rate operates on the second PLR Kirchhoff stress. That's also again used, but the concepts of all these rates are the same. Okay. So having completed objectivity, so we will now move to the actual constitutive equations. Next 3 to 4 classes, I will look at constitutive equations that are used basically for nonlinear elasticity. Okay, maybe should be able to complete it in the next 3 classes, and then we will come back and see the finite element formulations for large deformation problems. Okay, how we can extend the small strain problems to large deformation problems. Is that clear? Any questions? Okay. So if there are no questions, we will stop here and we will continue in the next class.